Good afternoon, everyone. Welcome to the second episode of our data science webinar series. Today, we're going to be having an introductory presentation on artificial intelligence. Last week, we talked about machine learning. We have the same presenters today as last webinar. First of all, we have Tom Marlow. He is the Chief Technology Officer here at Black Hills IP, and we're also joined by Manjeet Rege. Manjeet is the Director for Applied AI at St. Thomas University. A couple quick things. There is a Q&A panel on should be on your Zoom screen. You can utilize that if you have any questions throughout the entire webinar. We will get to those at the end. We love your questions, so please send those throughout the webinar. And second, there will be a copy of the slides as well as the recording sent out after the webinar to the attendees. So be on the lookout for that. Tom, I'll hand it off to you.
All right, thanks a lot. Tom Marlow here. And if you were with us last time, you'll know that I'm a patent attorney and Black Hills IP is a legal tech company. And of course, this is a webinar series about data science and artificial intelligence. I'd say this is a match made in heaven. You see, this is a very cool and interesting topic, and it's being sponsored by a legal tech company because, well, most industries these days are being impacted by the advances being made in computational intelligence and data availability, and frankly, the legal field is no exception. So in the spirit of accessibility, we want to try and break down this world-changing technology that ultimately will be impacting all of us. I'm joined again by Dr. Manjeet Rege, the renowned expert in data science and AI technology. So he gets to do the heavy lifting here. Thanks, Manjeet. Great to have you here again for our second session.
Sure. Thank you so much, Tom, and thank you everyone for joining us again today. So over the next 1 hour, I'm going to take you on an exciting journey talking about what is AI, and also kind of getting into the depths of some of the number of terms that we use: deep learning, neural networks, and limitations of AI, and other such things as deep fakes that you hear about in the media quite a lot. So let me first start off with the fact that a number of industries today are using AI, right? So more and more companies are allocating large R&D budgets for AI, and mobile and cloud, in the past decade played a huge transformative role at the enterprise level. In the years ahead, across different industry verticals, AI is expected to do something similar. Now, with all of this attention towards AI, is this something new? Is this something that was discovered in recent times? Well, the reality is AI has been around since 1950s. So if you look at this picture on the axis over here, AI has been around since 1950s, and then there are these subfields. So you have AI as a larger field. A smaller discipline within that is machine learning that helps you learn from data. And one particular type of technique, namely neural networks, and when you make those neural networks large and complex, we call them deep neural networks. And that is what we call deep learning, right? So you can think about this as a larger field, a smaller subset of this larger field, and this is a much more specialized subfield of machine learning. Although a number of times in marketing, you might hear people use the term artificial intelligence and machine learning and deep learning quite interchangeably. Now, let me quickly give you a background about AI. As I said, it's been around since 1950s. So in 1956, there was this conference that was held. researchers who were working in the field of AI, they wanted to develop computers that can mimic humans. So they were all working on different aspects of automation. So they decided to come together and at this particular conference and said, can we decide on an agenda that when we think about building computers that mimic AI, what are the things that we need to accomplish? So one such thing is reasoning, right? So something that a human has. So you are given a particular problem and you want to solve that problem, or you want to reason your way to the solution. Second was knowledge representation. So can we have computers know about the world around us so that we can ask computers questions such as what is a table, what is a car, what is a human, what is a dog? Third was, can we have computers do planning and navigation for us so that if I have to get from point A to point B, a computer should be able to help us, give us the best route based on the traffic around. Remember, all of this is in 1956. Then natural language processing, that is one another thing that we would like computers to do, is to learn how to speak a language and perhaps speak it back at us or understand what we are speaking. Perception, is it possible to teach computers sight and sound? That is, given a particular image, it can analyze that image or video or hear the sound, understand the sentiment. And one of the things that humans have is being creative. So can we have computers generalized intelligence? That is, if I am able to accomplish these building blocks, can we put those building blocks together so that a computer now has generalized intelligence such as creativity, emotional intelligence, and things of that nature? Now, this is the agenda that they set out to achieve back then. What happened over a number of decades since then is that AI went through a number of boom and bust cycles that we call AI winters. So there were long periods of time when initially, after showing a lot of promise, there was a lot of disappointment and people backed out from the funding and researchers kind of moved away. So one such promise was in early 1950s, where this was during the Cold War. There was an interest in translating English to Russian and Russian to English. And IBM did this particular experiment that they took 60 Russian sentences and translated that to English. Now it worked fine for those 60 sentences, but the meaning was not captured. So if you have used Google Translate today, and if you give English as the input, a sentence in English as the input, translate that to Russian, and then take the Russian translation that Google Translate gives you and feed it back into Google Translate to get your original English back, you would get the same English sentence back. But the way, the level of technology that we had back then was, if you gave a sentence like this in English and had it translated to Russian, so English to Russian, Russian to English, then what you would get back is this. So it was doing word to word translation, and the meaning, semantics was not being captured. And if you have a lot of these errors, then scalability becomes an issue. So after this initial promise of 60 sentences working out fine, it led to a number of long periods of time when the funding was cut. So there were some other approaches that people kind of quickly pivoted towards. One such approach was a micro world approach. That is, let's not get too ambitious and get ahead of us and try to solve this big problem about building computers similar to a human. Can we perhaps focus this automation on smaller domains? So in this particular approach over here, this researcher, he has these number of blocks, and you have this robotic arm that is taking instructions in, maybe pick a particular block, keep it on the floor, or pick up that and keep it on another block, following certain instructions. This is an application which is still, live. You can play around with it. That is trying to mimic how a talk therapist works. So if you play around with this, you can type your name, you can ask a question. But with both these applications in a micro world approach, because you're narrowing down your problem domain so much, the moment you drift away a little bit, the application doesn't respond. Even with this talk therapist application, you ask something which is a little bit too abstract or deep, the application does not know how to respond back. You give a particular problem to this robotic arm, which might be a little bit challenging in terms of putting these blocks on top of each other. It does not work well. So then in 1980s, there came a period where AI approach was based on expert systems, where the idea was, if our eventual goal is to build computers that are like humans, let's extract all of the knowledge that is there in humans and kind of code that up in computers. So if I, let's say, want to do a medical diagnosis expert system, let's interview a number of doctors and have all of that information coded up in a computer, so that when you present certain symptoms, it should then give you an answer back about what the possible diagnosis is. Now, it turned out that the accuracy was similar to a human, right? So you put all of this effort in, and if the achieved accuracy does not go significantly above what a human was able to provide, then all of that effort is perhaps not worth it. Secondly, another initial assumption was that if we are able to build these different expert systems, one for a doctor, one for a physicist, one for, let's say, a K-12 teacher, then perhaps we can build an ensemble of all of these and lead to that generalized human intelligence. And also the hope was, if I build one expert system, the startup time to develop another expert system would perhaps be lower. Turned out, every time you had to begin from scratch, and it wasn't really leading to that generalized human intelligence. So over these periods of time, as I said, it went through a lot of ups and downs, AI as a field. And recently you hear the term deep learning, which is based on a specific type of machine learning algorithm called neural networks. Now, the idea by itself is not new. It was initially proposed in late 80s, and there have been neural networks developed in late 80s that recognize handwritten digits of zip codes, for example. But in spite of that initial research, about 10 years ago, that a big major milestone was achieved. And that was this Google experiment in 2012. So what Google did was they took 10 million YouTube videos and extracted 200 by 200 still images from those YouTube videos. And they ran this data, or they processed this data on 1,000 computers with 16 processors on each. So you had 16,000 cores or 16,000 processors, and they allowed the algorithm to process these YouTube videos for 1 week, right? So that 10 million YouTube videos. Now, what happened was the algorithm was able to recognize a number of objects that appeared in those images. So out of the 20,000 objects that appeared, the algorithm were able to correctly recognize about 16%, that is more than 3,000 objects. So what was different here was that there was no human saying that this is how a cat looks. This is how the nose, eyes, or the paws look. All of that data was fed to a particular kind of a machine learning algorithm called neural networks with a lot of data, and the object recognition was learned automatically without any interviewing of experts. And what Google also discovered, that people love cat videos, and cat was one of the many objects that appeared in these YouTube videos. So deep neural networks, right? So what I talked about here was the underlying technique that was used was a neural network. When we refer to the term deep neural network, now we are talking about scaling it up. That is, you have large compute power, you have an extremely complex algorithm that is based on neural network, and you have large amounts of data that is being fed to these. So if you looked at traditional machine learning, it used to reach a plateau. So this axis, vertical axis, is the performance, and x-axis is the amount of data. So traditional machine learning, as you fed more and more amount of data, it used to plateau out. But with neural networks, so if you have a small neural network, think about small, medium, and large in terms of complexity or computational resources at your disposal, which we did not have in the past. These days, with cloud giving you access to virtually infinite compute power, with IoT, you have now lots and lots amount of data. And in the past, you were restricted by the hardware resources. Now, I don't have to invest in hardware. Now I can keep on spinning up more and more compute in the cloud. So I'm able to have large compute or large neural networks. So if you feed more and more data, you're able to achieve a higher accuracy. So this is what is different today compared to the initial disappointment that we saw more than 50 years ago. And if you look around, all of the software that you use, whether it is a news aggregator, whether it is the images that get backed up in your photo repository from your phone, automatically it is recognizing who you are, who your spouse is, who your friends are, recommendation, things that you might like, and also the price that you might want to rent out your room based on what is happening in that town at that particular time of the year. All of this has deep learning or a deep neural network behind the scenes. So Smart Reply is a Google feature. So based on the email that you get, it presents to you automatically 3 possible answers for you to select. A negative response, a positive response, and a neutral response. So this is a very complex model, right? So it is analyzing a sequence of words coming in, and based on that, it is giving you a sequence of words to as a response back. So I was traveling overseas, and my wife sent me a message saying that, hey, I got a job promotion. And below that, there was one such option over there saying that, great, congratulations, I'm proud of you. I just selected that, and she got the message back. Now, till date, she does not know that it was Google who enabled me to give that response. So that was an application of deep learning right there. Now, these initial goals that we spoke about, right? The reasoning, for example, and you might have heard about this AlphaGo, which is a deep neural network application that was playing against the human grandmaster in this board game Go. Now, Go is a 19 by 19 board. Now, turns out there are more possible moves, which is 10 to the power of 170, than there are atoms in the universe, which is 10 to the power of 80. So this is an extremely complicated board game, and a computer based on AI was able to beat a human. And these grandmasters, in fact, said that they became better players just by playing against a computer, because a computer initially had a very unconventional moves that it made. And as a result, a lot of people thought that it is in fact going to lose, but because of those unconventional moves, eventually it ended up winning. So this is the case of a human learning from a computer to become a better player, right? So that is the state of art in terms of reasoning. Second, knowledge representation was something else, the second goal that they had initially set out in 1956. So medical tasks that require a lot of human medical knowledge can now be done by deep learning. Medical image analysis for detecting and predicting tumors, examining, let's say, a blood sample to detect cancer cells, planning and navigation, right? So now, in terms of technology, I would say the problem is almost solved. Just a matter of regulation, whether we actually end up having fully self-driven cars on the road or not. But in terms of the state of art of AI, planning and navigation is something that AI is able to do. Natural language processing, if you give a complex sentence like this, AI is able to figure out that you're referring to the person, Paris Hilton, this is the city, Paris, this is the hotel, and this is the song. So natural language processing based on AI is able to understand the complexity of a sentence. Perception, right? So when you think about AI, one or an AI driving, navigating a self-driving car, one essential part of it is AI being able to detect and recognizing objects. It has to decide whether that's an image of a stop sign, whether it's a real stop sign, and how confident is it. Similarly, if you present to it a number of YouTube videos, it can do automatic indexing about where you are doing some chopping and things like that. So perception again, there have been a lot of advancement due to AI in recent times. Third, we spoke about creativity. Can AI help us generate new content? So I'm going to quickly show you this. Now, every time I am refreshing this page, you're seeing a new face. Now, all of these face images are generated by AI. These are not pictures taken of a real human being. These are artificially generated face images. They look very, very realistic. So in terms of creativity, this is just one such application, but I'm sure you have seen other applications as well, where AI has generated written text or sound, or you show one particular source image or a painting, and based on that inspired painting, it generates new content. Let me now talk about neural networks. What is a neural network? And I'll try and simplify this as much as possible. So what is the problem that we are trying to solve here? The problem that we are trying to solve is that of prediction. So if you have, let's say, data where you have X to Y mapping. So X is, let's say, features of a house, and Y is the price of a house. So let's say this is your data that you have collected of houses that have been sold. So what is the X here? X is living area, number of bedrooms, the size of the garage, area of the plot. And Y is the price at which the house was sold. So this is your training data. And if you build a model based on this, the next time a new house, let's say you want to sell, all you need to do is provide the X. And if the model has truly learned the relationship between X and Y, it can now predict what the price should be for listing the house on the market, right? So the problem is mapping X to Y. So that is what supervised learning is. Now, let me get to what a neural network is. So let's think about price and demand. So you have some instances of examples where as the price increases, you can see that the demand of the product that you're selling goes down. And if you build a model based on this, right, so that you can see that the demand cannot be negative, so you have a hard stop over here. So this is a model that is basically capturing the relationship between price and demand. And if I think about this again in terms of input to output mapping, that X to Y mapping, the X over here is the price and the Y is the demand, right? And this particular blue line or the model that you see is this processing unit that is learning the association between the price and the demand. So if you give me a new price, this particular processing unit that we're calling a neuron should be able to give you what that demand should be. So this is one processing unit, one input, one output. What if now I have multiple inputs? That is, I don't have just a price, but I have a number of things I want to consider. So for example, I might have price, I might have the shipping cost, I might have marketing, I might have material. So if I combine, let's say, price and shipping cost together, I end up figuring out how much affordable is this particular product. If I take into account the marketing of this particular product, I can probably come up with how much people are aware about our product. If I take into account the marketing and the material that is used, and of course the price, those three things, I can figure out what is the perceived quality of the product that I have. And then when people are willing to pay a particular price, right, for a product, they may have their own preferences. That is, to me, let's say affordability might be more important. So I might put more emphasis on that edge, less on this, perhaps a more on this. Somebody else might have an equal weightage to each one of them. And that determines what the eventual demand is. So in terms of that X to Y mapping, how many inputs I have 1, 2, 3, 4. And the Y that I'm trying to predict over here is the demand. 4 inputs, 1 output, right? And the difference here is that I do not have one single neuron doing the work. I have a layer of neurons, and whatever those neurons end up processing becomes the input to this particular neuron. Now, in terms of reality and the way this works when you actually implement in code is that you do not sit and combine these inputs and come up with affordability, awareness, and perceived quality. What you in fact do is you take your entire data and you have these different processing units, and you have certain initial edge weights, certain initial importance assigned randomly to each one of these edges. So I take the first example, the first row of my data where I have a price, I have a shipping cost, I have a marketing material, and then I see whether the prediction that I'm getting is correct or not. And these initial edge weights that I assign, I can then go back and fix them. So initially, I might just put some random values on each one of these and go through the network and see what is the output that my model is predicting. So if I expected a particular output, but my model is giving me a different output, which means my model is making an error. And why is it making an error? Because these edge weights that you have, those are not correct. And I need to go back and change those edge weights. So you go back, that is the algorithm goes back, changes the edge weights, and you keep on doing this forward, backward. So you're forward propagating, calculating what it is calculating is correct. If it is not correct, you back propagate and you fix those edge weights. It will reach a stage where your training is over, your neural network has learned how to, let's say, make a prediction. Similarly, for image recognition, it's a similar idea. You present each of these neuron layers an image and you tell what is in that image, another image, and you tell what is in that image. And each of these connections are initialized randomly to begin with, and you measure the output. So if you have a cat image and it is predicting a dog, which means these edge weights have to be changed. So it goes through this forward and backward a number of times, forward to measure what we are predicting, backward to fixing the edge weights. And it reaches a stage where it is able to make a correct prediction. That is, you give a new image now and it ends up making the right prediction. A quick example about how face recognition works. Let's say I have an image of a human face, and let's say this is an 8x8 image. It's actually larger, but just for the sake of discussion, let's say I have a 8x8 image. So I have a 64 inputs going in to my neural network. And all of these layers have been arranged in a particular order. That is, whatever these initial layers are analyzing and producing as an output becomes the input to the next layer. Whatever these one are analyzing and producing as an output becomes an input to the next layer. So the initial layer detects basic things from the image, such as contours, edges in the image. This becomes the input to this next layer that puts together all of these edges and contours and begins to form parts of an image. This becomes an input to the next layer in the neural network. That is when the faces begin to form, and eventually you have an identity of a person learned. Let me touch upon limitations of AI. With all of this buzz around what AI can or cannot do, what are the limitations of AI? So one maybe rule of thumb is, if there is something that one can do, a human can do, without too much deeper analysis, with a second of thought, you can probably automate that with AI, such as detecting spam emails, all of these, right? A self-driving car, right? So when you're driving a car, you're listening to music, you could be speaking to somebody sitting with you in the car. You're not involved in a lot of deep analysis. So these things could be done with AI. But if I ask you to do a market research study and produce a 20-page report, this is something that an AI cannot do, a human can do. Similarly, let's say you're trying to automate customer service and you receive an email like, the item I bought arrived late. It was for a retirement gift for a colleague. The item arrived after the retirement party. I would like to return it. Now, what an AI can do is it can quickly figure out what kind of a message is this? What is the sentiment in that message? And detect certain words and then automatically route it to the appropriate department. That is, this is for returns, and we need to help them quickly. What an AI cannot do is come up with a response like this that perhaps a human can do. Another example, in a self-driving car, it is extremely important to detect the objects that the camera is detecting or getting through the camera feed. So how far an object is and what is the confidence level of that particular object? Is it an image, a billboard? Is it a real object? AI can do that. What AI cannot do is differentiate between these three gestures. They all appear the same to an AI today, but a human can easily detect the difference between these three. How do you start AI projects? There's a common misconception that you have to wait a long time to collect large amounts of data before you can start getting value from data. And there is some truth to that, but you don't have to train your own model from scratch. All of the major cloud service providers, Azure, AWS, and Google, provide pre-trained models. So this is machine learning application programmer interfaces. So one such already trained model is a vision model. So from your code or from your application, you can call this particular vision model and you can give it an image. Let's say you have an e-commerce site where people are uploading images of products when they buy. You would want to make sure that that image is appropriate, right? So a Vision API provides you content moderation. So you don't need to have a human there. You don't need to even train your own model. You can just take an existing pre-trained model and take the images coming in, give it to this particular pre-trained model, and it can just tell you that yes, this particular image is fine. Similarly, in that email classification example that I spoke about, you have a natural language processing model. So this is again already pre-trained, available for you to use directly from your application. You can just take the content of text. If I'm, let's say, analyzing reviews posted on my website, it can quickly tell me the sentiment, positive or negative. If it is negative, I can then have the second level of check. What is the level of sentiment? How negative is it? Is that something I can fix, perhaps? Again, without training your model from scratch. So yes, having data is great, but without having lots of data, you can initially build some simpler models by calling upon these existing pre-trained models. So that's the first point. Second is, a lot of time, a common question is, where do we start? And one simple approach is find a particular task that is repeatable and perhaps a human is doing it. And if by automating it, I can see certain value from it, right? I might perhaps use that as my first initial use case. Having few initial easier use cases, you build a confidence and you get everybody's buy-in. Furthermore, if you want to build an AI team in-house, that is the way to go, because you have somebody internal that is able to understand what the problem domain is, and as a result can get you more value quickly. And everybody needs to be at the same level of understanding about what role AI is playing at the enterprise level. Having a strategy about how do we plan to use AI in the long term is extremely important. So strategic AI vision will involve a number of these aspects. Acquiring the data. A number of times you see free services being offered, and the premium service you're paying a price on, because the free service is a way to collect your data. And then once you have the data collected, you can probably refine your product and offer a premium service. Right? So one of the things that we always say in data science is that whenever something is offered, whenever a product is offered to you for free, you as the user are the product, because your data is being captured for monetization later on. Waiting too long to build a large IT infrastructure so that you can do AI later on is not the way to go. Probably having both these together, that is having an AI team and the IT infrastructure team growing together, so that if the AI team realizes that the data that is collected is not as great, they can give that feedback to the IT infrastructure, and accordingly they can collect the correct data later on. Also, very important is a lot of time, 70 to 80% of the time needs to be allocated for cleaning and prepping the data. So that strategic data acquisition, this is an important part that you need to also account for. Let me talk about AI in the real world, model bias and things like that. So this is from one study that they had a web scraper. So basically an AI learned from the text available on the web. And once that AI model had learned the text available on the web, if you asked a question like what man is to a woman as father is to a what, it would reply a mother. Man is to a woman as king is to a what, it would reply a queen. What man is to a computer programmer as woman is to a what, it would reply a homemaker. So this is because of the stereotype that existed in the text that the model learned from. And you see a number of these biases in a number of tools. This was in the news recently where Apple's credit card gave a higher credit limit to the husband, but a lower credit limit to the wife. Here is another example of gender classification. In this study, it showed that if you have darker skinned subjects, the level of error was extremely high. But for a lighter skinned, the level of error was extremely low. Amazon's facial recognition system that they were selling to police had similar biases to what we showed in the earlier slide. And there was a lot of backlash about that. And I think Amazon then later on backed off from that. Here is one such small video by Dr. Joy Buolamwini that talks about limitations of AI when it comes to recognizing women faces. Let's take a quick watch.
My heart smiles as I bask in their legacies, knowing their lives have altered many destinies. In her eyes, I see my mother's poise. In her face, I glimpse my auntie's grace. In this case of deja vu, a 19th century question comes into view. In a time when Sojourner Truth asked, "Ain't I a woman?" Today, we pose this question to new powers, making bets on artificial intelligence, hope towers. The Amazonians peek through windows blocking deep blues as faces increment scars. Old burns, new urns, collecting data chronicling our past, often forgetting to deal with gender, race, and class. Again, I ask, ain't I a woman? Face by face, the answers seem uncertain. Young and old, proud icons are dismissed. Can machines ever see my queens as I view them? Can machines ever see our grandmothers as we knew them? Ida B. Wells, data science pioneer, hanging facts, stacking stats on the lynching of humanity, teaching truths hidden in data, each entry and omission, a person worthy of respect. Shirley Chisholm unbought and unbossed the first Black Congresswoman, but not the first to be misunderstood by machines well-versed in data-driven mistakes. Michelle Obama, unabashed and unafraid to wear her crown of history, yet her crown seems a mystery to systems unsure of her hair. A wig, a bouffant, a toupee, maybe not. Are there no words for our braids and our locks? Does relaxed hair and sunny skin make Oprah the first lady? Even for her face well known, some algorithms fault her, echoing sentiments that strong women are men. We laugh, celebrating the successes of our sisters with Serena smiles. No label is worthy of our beauty.
So that gave us an idea about limitations of AI in the real world. Let me show you some other examples. Now, an image like this, where the actual label for this is a hummingbird, if there are minor pixel level perturbations done, that is something that you cannot, let's say, notice with a naked eye, but it can definitely fool an AI. An AI says this is a hammer. Similarly, for an image like this, you perform some pixel level manipulation, which a human again cannot detect. Those images look identical, but an AI gets fooled and says this is a desk. Similarly, this is Google's image classifier called the Inception version 3. So you take an image of a cat and you rotate the head a little bit, it says this is a guacamole. But you rotate the head to the left, it now says this is a cat. Again, a human will not get fooled so easily. This is an example of 3D objects, specially manufactured, that fool an AI. So this is a 3D manufactured, and you can see that it is predicting a rifle as opposed to a turtle. So this has been manufactured in such a way that the AI gets fooled, but a human does not. Here are some other examples, specially manufactured baseball that gets classified as an espresso. These are frames that when you wear them, AI says you are the actress Mila Jovovich. These are some stickers that you put on top of a stop sign, and the AI does not detect the stop sign at all. So think about a self-driving car. Somebody puts these stickers, that stop sign is not visible to AI anymore. Then we have deepfakes, right? So high quality deepfakes basically use AI to learn certain visual and oral characteristics about a subject, and then maps that information onto, let's say, another subject. So here is a deep fake of Mark Zuckerberg.
I wish I could keep telling you that our mission in life is connecting people, but it isn't. We just want to predict your future behaviors. Spectre showed me how to manipulate you into sharing intimate data about yourself and all those you love for free. The more you express yourself, the more we own you.
Here is another one.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele.
Here is another one. Beckham here speaking nine languages to fight against malaria. This was again done with his permission.
Malaria isn't just any disease. It's the deadliest disease there's ever been.
Se dice que ha matado más de la mitad de la población que ha existido.
وما زالت تقتل طفلا كل دقيقتين.
So I'll not go through the entire one. Here is a Nixon deepfake video that does not use an impersonator voice, but this actually uses a synthesized voice.
Good evening, my fellow Americans. Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace.
Now, not everything that you see is deep fake. There have been, I'm pretty sure you have seen this in the news, Nancy Pelosi's video, and also there was another video where CNN's reporter was accused of, I think, pushing the White House intern. Now, these were just video editing, where the video was slowed down and it wasn't deep fake. So not everything that you see is deep fake around you. So this has large repercussions where here is an example where the CEO of one British company received a call from the head of his parent company, and it was actually a deep fake synthesized voice of his boss saying that, could you please transfer $250,000? And he ended up doing that. This is another example of a deep fake that led to an unsuccessful military coup and destabilized the nation. This was in Africa, country, I think Gabon. This was a president who was not seen in public address for a long time, and the government released a video of him. And many experts who saw that noticed that his facial expressions were different, his eyes were not blinking and things like that. And that led to a lot of disturbance in that country, right? So there are these repercussions that can happen where you might have somebody saying something and then later on denying it, saying that it was actually a deep fake video, or you might have a deep fake video and the person might not have actually said anything like that. So very quickly, I'm going to end within a minute here. There's a lot of debate over AI and jobs, and there are these estimates about jobs getting created and jobs getting displaced. So in this particular study, what you see is the probability of getting displaced by AI. So higher you are in this list, there is a higher risk of getting displaced. Lower you are, lower is the probability. Right? So if you look at some of the heavy lifting jobs are higher in the list, and if you're in the legal or the legal tech world, you're probably safe. So I want to draw a distinction between getting displaced by AI and getting exposed to AI. If you embrace AI and if you make use of AI, you can stay ahead of the curve. And here is an article that I wrote that is available that talks about how law firms can embrace AI and stay ahead of the curve. So with that, I'll hand it back over to Tom, who will wrap this up and speak a little bit about what Black Hills does with AI as well.
Thanks, Manjeet. And I'm happy to see the legal industry low on that list, and that's kind of the way we approach things here at Black Hills as well, in that it's not displacing the folks that we have, but more so helping make those jobs easier and allowing people to do kind of the more, say, human thought intensive expertise leveraging things. And it's also, I think, worth noting, opening up more job openings on the kind of quasi-legal, quasi-technical kind of merged type of fields, automation specialist, DevOps, that type of thing seem to be places where we're hiring ideally folks with legal backgrounds or IP backgrounds in docketing and paralegal, but who are interested in getting involved on the more of the technology side of things. I think there'll be a lot more development there for folks that are interested. Now, to Dr. Rege's point on starting AI projects, I think it's worth stressing, and I'm going to share a quick example here about a couple of things to keep in mind. One is, obviously, it's important to have data. And the second piece is that data alone isn't always particularly useful. You either have to train a model or be able to leverage, like Dr. Rege mentioned, some of the growing off-the-shelf pre-built model capabilities that are out there, and finding the right one to kind of fit your project. So I'll give an example here of how we use some of this data at Black Hills IP and document identification. So we've been doing docketing for a little over a decade or so, and thankfully this has been computer assisted from day one. Now, even though we weren't fully automated in the early days, we processed through systems that drove our workflow and recorded the data. So to point one, it's helpful to have the data, right? And then the key is, whenever a document was identified by one of our expert docketers, we would store that data with the document. So that's your point two. Data alone isn't always enough. So here we're talking about years of categorized data. And now we're talking about something that can be used to train as well as to test models. The testing piece is important as well. So in addition, then before jumping straight into machine learning, we built an extensive set of expert systems. These are like rules based. So we could see if the document had X, Y, and Z, then it was this thing. And if it had A, B, and C, then it was another thing. So a lot of rules to identify these things was kind of the next step off of just pure human interaction. And these can be really useful. And if you build some of them, they can also help validate some of the ML models that you put together. And frankly, in many cases, you might find that these two systems work together really well, each having kind of strengths in different areas. So when beginning a project like this, you're going to want to take a look at the data that you have on hand, take a look at how well it's kept, maybe is the word. Do you have categorized or labeled data? I can't stress enough Dr. Rege's point regarding communication between AI teams and the IT team to make sure the data that you're managing is optimized for training, it's categorized consistently. It's easy to store a whole bunch of data and do a big project around it, and then have it not quite ready for training your machine learning models. But look, if you don't have well categorized data on hand, what can you do? There's some options. One is start setting up those processes to saving categorizations as part of your ongoing process. No time, kind of like the present. You can also jump in on a big, kind of sometimes boring project to sort, categorize, or label the data that you do currently have. I guess one thing to note as you're going through a project like that, you may be able to develop some rules to guide the categorizations. And again, like expert system rules, those can be useful. In some cases, I've seen the use of overbroad rules to categorize, and then maybe leveraging machine learning models to identify outliers. There's a lot of little kind of tricks of the trade that can be leveraged in this process, and that's where it can be really useful to have someone or a team that's dedicated on this that can really try and find what will fit the data that you have. And it can be kind of time taking at first, so that dedication is important. And so that's something to think about when starting your projects. We've been working on these things for years at Black Hills. Sometimes they work exactly as expected. Sometimes you get results back that require a little bit more work. So be patient with the process. With that, I'm gonna, because we're already a little over an hour. I'm glad it was more of Dr. Rege's time than my time. Very, very interesting presentation today. Thanks, thanks, Manjeet.
Thank you.
Yeah, and so I'm going to see if we have any questions before we depart. Let's see. Oh, okay. Here's one for if you have to do a categorization project, looking at old data that you've kept. Can that be successful? Any thoughts or advice on this part of the process? Manjeet, have you must have seen cases where folks have stores of data, but it's uncategorized, and then do projects to go back and categorize it to drive models.
Right. So it depends on how you want to address it. One way is to treat it like an unsupervised learning problem and do clustering based on that. If you, so that is kind of deriving groups on your own. But let's say you have predefined categories, then I think an easier way to do that is take part of the data and label it and say, this is one category, this is the other. And perhaps labeling your entire data set might be challenging, but I might take a little bit of data, label it, use it as my training set, and then the remaining unlabeled data, I will then put it through the model and then generate labels based on that. So the remaining data where I do not have which category it belongs to, my model can predict the label, and then I'll do a check whether it is getting it correct or not. If it is getting correct, then I'm generating the labels, and then I'll retrain my model with this new label data and then keep going that way. I don't know if that was confusing, but
kind of like an iterative process where you supervise what's
being predicted.
Yeah, that makes sense. All right, I think that covers us for the questions that we had today. Thanks, everybody. We'll have the third session for this coming up in, I believe, June.
June. Yeah.
So we look forward to the next session, and everybody have a great spring.